Okay, hello, welcome to the solutions for assignment 4. Question 1 here. The person in the diagram below has a full height of 175 centimeters. I will mark that down here first. So 175 is the full height, and the distance between their eyes and the top of their head is 15 centimeters. So I'll mark that down as 15. That means that the rest of their height must be the 160 centimeters. And the mirror that they are looking into is the smallest possible mirror that allows them to see their whole body. Part A, at what height must the bottom of the mirror be? So, seeing as how the light ray has to leave the foot and go into the eye and bounce off the mirror, we know that it's going to reflect off the mirror. Because of this, we know the law of reflection applies, so my angle of incidence is going to be equal to my angle of reflection. So if I actually extend this out and draw a full triangle, a full big triangle here, I will get a big right angle triangle, two of them actually, formed by this light ray and the person right here. So two big ones. We know that they are both right angles on the inside. We know that these two angles are also equal, which means that these two angles are also equal, which means that these are similar triangles. They're actually just identical. They are reflected across this line here. So they are identical triangles. That means that this distance and this distance have to be equal. So if I'm going to call one of these H1 and one of these H2, I can confidently say H1 equals H2. These are both the same length altogether. And we also know that this total height distance is 160. So we know that half of this distance is 80, which is also the height above the ground that the mirror is. So we know that this distance on the left is 80 because that is half of our 160. And we also know that that is the same height off the ground that the mirror is. So our calculation just ends up being 160 divided by 2 equals 80 centimeters off the ground for part A. For part B, we are going to essentially use the exact same logic just on the upper part from the person's eyes to the top of their head. So it's going to be the same math of 15 divided by 2. That equals 7.5. However, the top of the mirror is obviously not 7.5 centimeters above the ground because the bottom is 80. It's going to be 7.5 centimeters above the person's eyes is where the mirror is going to be, the top of the mirror. And we know that the person's eyes are 160 centimeters off the ground. So we're actually going to take 160, add it to the 7.5 that we just got, and we're going to get an answer of 167.5 centimeters for part B. And lastly, for part C, what is the length of the mirror? We're just going to go ahead and subtract the height of the top of the mirror, and subtract the height of the bottom of the mirror off of it. That will give us 87.5 centimeters. Great. Something to note, this is exactly half the height of the person. Okay. Moving on to the next one here. Show that when an incident light ray reflects off two mirrors at a right angle, that the reflected ray leaves parallel to the incoming ray. See the diagram below for reference. Okay, great. So we are given this diagram here for reference. And something we know is that these are at a right angle, these two mirrors. Something else we know is that these normals, even though they don't exactly look like it, but they are normals, which means they are also right angles to the surfaces here, which means that if I continue these normals, we create a rectangle, and the two normals have to be perpendicular to each other as well. So we create a little right angle triangle in here like this, with angles of theta 1 and theta 2. So redrawing this a little bit bigger, we have a right angle triangle with theta 1 and theta 2 here inside. So that means, therefore, all the angles inside have to add up to 180 degrees. So I have my right angle plus theta 1 plus theta 2 is equal to 180 degrees. I'm going to subtract 90 from both sides, and I get that 90 is equal to theta 1 plus theta 2. So I know that for a fact. This is an equation here. I also know that from this diagram, the light ray undergoes 4 different angle changes here, redirections. So the angle, we're told about the light ray's path in the form of 4 different angle measurements. First measurement is theta 1, second measurement is also theta 1, third is theta 2, fourth is also theta 2. So we know the light ray bends an angle of theta 1 plus theta 1, and then it bends another angle of theta 2 plus theta 2. So I'm going to go ahead and add all of those up together, all the angles that the light ray is described as being bent by or reflecting at. So theta 1 plus theta 1 plus theta 2 plus theta 2. Now I'm going to do a little bit of rearranging here. I'm going to say that theta 1 plus theta 2 plus theta 1 plus theta 2. I'm going to say it equals that. Just rearranging, swapping the two middle ones. And if I just draw in some brackets, just to really focus on the two halves here, just to really focus on them, we see that in the first bracket we have theta 1 plus theta 2. I know that that is equal to 90 from above. So I'll replace that with 90. And that's being added by another theta 1 plus theta 2. So that's another 90. So I end up with 90 plus 90 equals 180 degrees. So this here tells me that after the light ray has reflected off both mirrors, its direction has changed by the angle theta 1 plus theta 1 plus theta 2 plus theta 2. And I know that that angle is that all 4 of those individual angles make up the angle of 180 degrees. So therefore, the reflected ray must be, and I will say anti-parallel to the incident ray. The reason I don't say parallel is because parallel, I guess, would mean that they're also pointing in the same direction. Anti-parallel does not mean perpendicular in this case. It just means that they are parallel, but they point in opposite directions, which we can clearly see on the diagram here. So that was the answer for question 2 here. Question 3, draw 2 or more light rays to complete this ray diagram to find the image location and determine the salt image characteristics of the image. And then there's a little sentence telling you what side is the reflective side. I have my answer here, so I will erase that quick. Oops, forgot to erase that earlier. Okay, so I'm going to start by drawing my horizontal line that's parallel to the optical axis, and this will reflect off going through the focal point. So it will reflect off and look something like this. Next, I'm going to draw my line that goes through the focal point. No, I'll draw that one that goes through the center point first. Any line that goes through the center point just gets reflected back the way it came from. So that's how it travels. And the last one goes through the focal point here, and it gets reflected off parallel to the optical axis, so it's just the opposite of the red line. Okay, great. But the problem here is that the red, green, and blue reflected lines will never, ever, ever converge. They are diverging. So we need to trace back the virtual light rays. So that is what these dotted lines will represent. The virtual light rays. And the last one here, the red one. Now it's not perfect because my diagram isn't perfect, but that's okay. And here we see that my image is probably somewhere in here. Somewhere in there. And so this is a big part of the reason why I said just draw two or more, because when you're copying this down on a piece of paper to write your answer, it's not going to be perfect. The lines aren't going to line up perfectly. You're going to have some sort of mistake in there. But if you have just two lines, it makes it pretty clear where the image is going to be. For our salt image characteristics, the image is clearly smaller than the object. It is upright. It is between the mirror and focal point, and it is virtual. We had to trace back virtual light rays to create it, so it is a virtual image. So that was number 3. Number 4, oh, I did the same thing. Forgot to get rid of the answer again. Okay, same idea. Trace the light rays. What are the salt image characteristics? Start with my horizontal one. And this one gets reflected through the focal point. There we go. And, well, you already saw where the answer is. So I will trace back my virtual light rays here as well at the same time. Okay. My second light ray is coming from the focal point here, and it reflects off parallel to the optical axis. And the blue one comes from the center of curvature. This one looks like it worked out much better than the previous. for where my image is. So there we go. Looks like that one worked out much better. I guess I just drew my lines better. So my salt image characteristics, this is clearly bigger or larger, whatever you want to write. The image is clearly larger than the object. It is upright. It is right of the mirror. And it is virtual. Again, we had to trace the virtual light rays to find this image, because the real light rays were diverging. So that's question 4 done. Question 5, which is the last question here. A spherical mirror has a radius of curvature of negative 24 centimeters, and an object is placed 18 centimeters in front of the mirror. Part A, calculate the focal length of this mirror. So the focal length is just equal to the radius of curvature divided by 2, which is negative 24 divided by 2. So we get a focal length of negative 12 centimeters. There we go. B, is this a converging or diverging mirror? This is a diverging. We know this because focal length is negative. Calculate the image distance. Okay, so this is where we're going to use what is effectively our thin lens equation here for the mirrors. DO, 1 over F equals 1 over DI plus 1 over DO. So plugging in our values, we are going to get 1 over negative 12 centimeters equals 1 over DI plus 1 over, I believe it was 18 centimeters for the object distance. Yes, it was. And doing a bit of rearranging, I'm going to subtract 1 over 18 from both sides. And punching this into my calculator is going to give me something. 1 divided by negative 12 minus 1 divided by 18 equals negative 5 over 36. And now I'm going to flip both of these, so I get DI over 1 equals negative 36 over 5. This is just DI equals negative 36 over 5, which is a perfectly valid answer, but sometimes it's more useful to see this as a decimal. So this is negative 7.2 centimeters. So that is our image distance. The magnification, we have 2 formulas for this. One of them involves image height and object height. We don't know either of those, so we're not going to use that one. We're going to use the one that we do know, which is image distance and object distance. So our image distance that we just calculated was negative 7.2. That's going to be over our object distance, which is 18. Again, all of this is in centimeters. Our negatives cancel out, so we just get 7.2 divided by 18, which is exactly 0.4 as our magnification. Again, magnification has no units. The centimeters cancel out here. And lastly, what are the salt image characteristics? Our magnification is between 0 and 1, so this is smaller. Our magnification is also positive, so this is upright. the location. Now, if you don't remember how to determine if this is left or right of the mirror, please use an awesome free open sourced simulation like PHET, Geometric Optics here. So when you come to it, select mirror, select the mirror type that you have. In this case, we have a convex mirror, diverging mirror, and align your object to how your specific scenario is working out. For us, we have our object outside of the focal point, so I will drag it much farther away than the focal point would be, the focal distance, and we see that the image is on the right hand side over there. So we know that the image will have to be right of the mirror, and because the image is on the opposite side of the mirror as the object, this is a virtual image. So that was everything for assignment 4. If you have any questions, please feel free to email me or ask me in class. Thank you.